This asteroid weighs about half of what it should. That single stubborn number is the first clue that the closest asteroid in recorded history is not what anyone expected. Its name is Apophis, and in 2029 it will pass closer to Earth than our own satellites, close enough for 2 billion people to see it without a telescope. It will not hit us. That is ruled out for 100 years. But it is a loose pile of rubble with a weak point built into its middle, and our planet's gravity is about to grab it. What happens when Earth squeezes a mountain that is barely holding itself together? By the end of this, you will know exactly why scientists cannot look away. Drop a comment. Will you be somewhere? Apophis lights up the sky in 2029, or watching the feeds with the rest of us? Subscribe so you do not miss the moment it develops. Now, let's get into it. On the 13th of April, 2029, an object the size of 3 football fields is going to pass closer to Earth than the satellites you rely on every single day. It will slide in beneath them, over the Atlantic Ocean, close enough that roughly 2 billion people will step outside and watch it cross the sky with nothing but their own eyes. No telescope, no special equipment, just a moving point of light, brighter than the stars in the handle of the Big Dipper, drifting across the dark. And here's the part I need you to hold on to from the very beginning, because everything that follows depends on it. This asteroid is not going to hit us. That has been ruled out with confidence for at least the next 100 years. So this is not a doomsday story. It is something stranger than that. And in some ways, it is more interesting, because the closer scientists look at this rock, the less it behaves the way a simple rock should. The asteroid has a name. It is called Apophis, and on that April night, it is going to pass about 1,600 kilometers above the Atlantic. To understand how close that really is, you have to know where our satellites live. The ring of satellites that carries your television, your weather data, and a huge share of global communications sits at roughly 35,700 kilometers above the planet. Apophis is going to come in underneath that ring. It will pass at about 1/10 of the distance to the moon, and it will be the closest predicted approach of an asteroid this large in the entire recorded history of the human species. This object is not small. Apophis measures somewhere between 340 and 375 meters across, about the length of 3 football fields laid end to end, closer to a skyscraper lying on its side than to anything you would call a pebble. For one night, people across Europe, Africa, and Western Asia will look up and see a mountain of rock pass overhead. And for once in our long history with these objects, the public will not read about it the next morning. They will witness it happening, live in the moment. But the reason we are here is not the flyby itself. The reason we are here is what the flyby is going to do. Because in 2029, our own planet's gravity is going to reach out and squeeze this asteroid in a way nothing has in millions of years. Nobody can tell you exactly what will happen when it does. And that uncertainty, that single honest gap in our knowledge, is why the people who study this thing are quietly on edge. So let me show you why a rock we have measured so carefully has become the most interesting object in the sky, and why the calmest scientists in the room get a little tense when you ask them what happens next. To understand why the object matters more than the orbit, you have to go back to the moment Apophis first frightened the entire field of astronomy. The asteroid was first detected in 2004. Within months, the people calculating its path watched the impact probability for 2029 climb to about 2.7%. Now, 2.7% does not sound like much, but for an object this large on a date this specific, it was alarming enough to set a record that still stands. On the scale astronomers use to rate asteroid threats, a scale that runs from a calm green 0 all the way up to a certain catastrophe, Apophis reached the highest level ever assigned to any asteroid, before or since. For a short and very tense window, this was the single most dangerous rock humanity had ever found, and it already had a date attached to it. Try to sit inside that moment for a second. because it is easy to skip past the human part of it. Astronomers are, as a group, some of the most measured and careful people you will ever meet. They do not panic easily, and they are professionally allergic to overstatement. And yet, here was a number, climbing month after month, on an object large enough to flatten a region if it ever came down in the wrong place. Every new observation could have pushed the probability up or down, and for a while, nobody knew which way it would go. The threat scale they use is built so that the average person can understand the danger at a glance, running from a calm 0, meaning no concern at all, up through the levels that demand attention, and finally to the top, which means a certain collision with global consequences. Apophis did not reach the top, but it climbed higher than anything ever had, and it did so with a specific year printed next to it, which is a very different feeling from a vague someday. That is the emotional backdrop you need to carry forward. This asteroid earned its reputation honestly. It is not a rock we are inventing drama around. It genuinely frightened the people best equipped to judge it, and that history is part of why its strange behavior now commands so much attention. Then, the science did exactly what science is supposed to do. Astronomers kept watching. They kept tracking the asteroid across the sky, refining its path a little more with every observation. And in 2021, they used powerful radar to pin down its trajectory with extraordinary precision. The result was a clean, unambiguous, all clear. An Earth impact was ruled out for at least 100 years. The small, lingering chances of a later strike, once whispered about for 2036 and 2068, dropped to nearly nothing. We now know where Apophis will be in 2029 down to the kilometer. The rock that once held the record for most dangerous object in the sky had been declared safe. And that is exactly where the real story begins. Because knowing the path of an asteroid is not the same as knowing the asteroid. We have measured the orbit of this thing better than almost anything else of its kind. We have barely measured the object itself. Think about that gap for a second. We know its address with almost perfect confidence. We do not know its character at all. We can tell you precisely where it will be on that April night, and we cannot tell you what it will do while it is there. For most of the time, Apophis has been sitting in our catalogs. That gap did not matter. Nothing was going to disturb it, so its inner nature was a curiosity, and nothing more. In 2029, something is going to disturb it. Our planet is going to grab hold of it. And so the question quietly changed. It stopped being, where is it going? A question we have answered, and it became something we cannot answer from a desk. What is this thing actually made of on the inside? And what happens when Earth reaches out and squeezes it? The first clue that the answer would be strange came from a single stubborn measurement that simply refused to make sense. The first thing that told scientists Apophis was not an ordinary rock was that it weighs far too little for its size. Density is one of the most powerful numbers you can measure about an asteroid, because density tells you what a thing is made of and how tightly it holds itself together. When you measure the density of Apophis, you get a number of about 1.75 grams per cubic centimeter. Now hold that against solid, stony rock, the kind of rock you would find in a mountain here on Earth. That runs closer to 3 grams per cubic centimeter. Apophis is barely more than half as dense as the rock it is supposedly made of. And there is really only one good way to explain a number like that. The asteroid cannot be a single solid boulder. It simply cannot be. If it were one continuous piece of stone, it would weigh far more than it does. To be as light as it is, Apophis has to be full of empty space. When scientists put a number on that empty space, on what they call the porosity, they land at around 40%. Let that sit with you for a moment. Almost half of Apophis, by volume, may be nothing at all. Not rock, not metal, just gaps and cavities and hollow pockets threaded through the entire body. That is the signature of what scientists call a rubble pile. And the phrase means exactly what it sounds like. The picture in your head is probably one clean mountain of stone hurtling through space. Throw that picture away. What is actually coming toward us on that April night is a loose heap of gravel, boulders, sand, and dust. Thousands of separate pieces, held together not by any glue, not by any solid frame, but almost entirely by their own faint gravity. A rubble pile is closer to a floating pile of sand than to a stone. It is held together by a grip so weak that a strong enough tug from the outside could genuinely rearrange it. And in 2029, Apophis is going to get exactly that kind of tug from the largest object it has ever come near. We are not guessing about any of this, by the way. This is not a scientist waving their hands and saying it is probably hollow. We have gone out and visited objects exactly like Apophis, and we have touched them. When Japan's Hayabusa spacecraft flew all the way out to a small asteroid called Itokawa, it found a rubble pile, a jumble of loose material with almost no solid core to speak of. Apophis closely matches Itokawa in the ways we are able to measure. Then, when NASA's OSIRIS-REx mission reached out to touch the asteroid Bennu to grab a sample in 2020, something happened that surprised everyone watching. The surface behaved like a pit of plastic balls. The spacecraft sank into it, farther than anyone expected, and had to back away. These objects are not the solid mountains our imaginations insist on picturing. They are flying rubble, barely holding themselves together. And Apophis, our record-breaking visitor, appears to be one of them. It helps to understand where a body like this even comes from, because a floating pile of gravel is not the obvious thing you would expect space to produce. The solar system is an old and violent place. For billions of years, objects have been colliding, shattering, and drifting back together in slow motion. When two solid asteroids smash into each other hard enough, they do not always vaporize. Sometimes they simply break into countless fragments, and then, over enormous spans of time, the faint gravity of all those pieces gently pulls a portion of them back into a loose clump. What you get at the end is not a rebuilt mountain. It is a heap, a gravitational bag of debris, with all the gaps and voids and hollow pockets left over from a reassembly that was never tight to begin with. That is almost certainly the life story of Apophis. It is not a single ancient stone. It is the reassembled wreckage of older collisions, held together by nothing more than its own weak pull. And that 40% of empty space is not a small technicality either. Picture cutting the asteroid in half and finding that nearly half of what you are looking at is simply nothing, just the dark spaces between boulders and grains. A structure like that has almost no internal strength. It cannot resist being pulled or twisted the way a solid body can, because there is barely anything holding one region to the next. This is the physical reality that makes the 2029 encounter matter so much. We are not sending our planet's gravity against a hardened mountain that will shrug it off. We are sending it against something closer to a loosely packed snowball, and asking what happens when a world takes hold of it. Now, that fact alone, the fact that the closest asteroid in recorded history is essentially a loose bag of gravel, would already make the 2029 encounter worth watching. But the density was only the first strange thing. When scientists finally got a real look at the shape of this object, it stopped being merely light. It started to look almost deliberately fragile, and you are about to see exactly where its weak spot is. When radar imaged Apophis during its 2021 approach, it produced the first genuine look at the asteroid's shape, and the shape was not a simple potato. Most people, when they imagine an asteroid, picture a lumpy oval, a sort of cosmic potato, tumbling through the dark. Apophis is not that. It came back elongated, pinched tightly in the middle, with two distinct lobes joined by a narrower neck. The scientists who described it kept reaching for the same handful of words. It looks like a peanut. It looks like a dumbbell. It looks like two rocks stuck together. And that last description is not a joke. It is almost certainly the literal truth. That shape has a name. We call it a contact binary. And the story behind a contact binary is quietly remarkable. Long ago, two separate bodies drifted slowly toward each other through space. They did not smash together in a violent collision. They came together gently, almost tenderly, touched, and then simply stayed touching, held against one another by their own faint gravity ever since. So when you look at Apophis, you are not looking at one object. You are looking at two, pressed together at a single point, traveling as a pair. And this, remember, is a body already made of loose rubble to begin with. Two piles of gravel, leaning against each other in the dark. It is worth pausing on just how gentle that joining had to be. If those two piles of rubble had come together with any real speed, they would have destroyed each other, blasting apart into a new cloud of fragments. For them to touch and stay whole, pressed together instead of shattered, they had to drift into contact at a crawl, slower than a person walking. That tells you something quietly important about the grip holding Apophis together today. It is not welded. It is not fused. It is the faintest possible embrace between two objects that barely had the strength to hold each other in the first place. And that same barely there grip is what has to survive an encounter with Earth. This kind of shape is not actually rare. Roughly 15% of the near-Earth asteroids larger than 200 meters show this same two-lobed form. Once you start looking, they turn up everywhere, which tells us that whatever process builds these gentle two-piece bodies is common across the solar system. But common does not mean safe, and here is why this particular shape matters so much for what is coming. A contact binary comes with a built-in weakness. It has a flaw designed right into its structure, and that flaw is the neck. Think about anything you have ever held that was made of two pieces joined together. A cheap toy, a tool with a handle, anything welded, glued, or fused at a seam. Now ask yourself, where does a thing like that break? It does not break through the solid middle of either piece. It breaks at the seam. It fails exactly where the two parts meet, because that join is always the weakest point in the whole structure. The neck of Apophis is its seam. It is the narrowest, most fragile part of the entire body, the thin waist where two separate worlds are pressing against each other with the gentlest possible grip. And a seam becomes dangerous the moment something starts pulling the two pieces in different directions. I want you to hold that image because it is going to matter enormously in a few minutes. In 2029, when Earth's gravity reaches out and takes hold of this asteroid, it is going to pull hardest at exactly that point. Not evenly across the whole body, hardest at the weakest spot. The shape of Apophis is not just an interesting curiosity for a slideshow. It is a map. It is a map of precisely where this asteroid is most likely to give way. And as it happens, the way Apophis moves through space points at the very same conclusion. Because this object does not spin the way a normal object should. Most objects in space, if you leave them alone long enough, settle into a simple, steady spin around a single axis, the way a planet turns smoothly on its pole. It is the natural resting state of a rotating body. Apophis does not do that. Apophis tumbles. It rotates around more than one axis at the same time, so that it wobbles and rolls as it travels, never settling into a clean, predictable spin. There is a main rhythm to its tumble that takes about 30.6 hours to complete, and layered on top of that main rhythm is a slower wobble that takes around 263 hours. So the motion is not one turn. It is two motions tangled together, a spin inside a wobble. There is a reason a clean, single-axis spin is the normal resting state, and understanding it makes the tumble even stranger. Over long enough time, a rotating body tends to shed the energy of any wobble, gradually settling into the most stable, lowest energy way of turning, which is a smooth rotation around one axis. It is a bit like a spinning top that starts out lurching and slowly steadies itself as it goes. So when you find an object that is still tumbling, still lurching through two motions at once after all this time, it usually means one of two things. Either something disturbed it relatively recently, knocking it out of a settled spin, or its internal structure is so loose and irregular that it resists settling in the first place. For a loosely bound rubble pile like Apophis, that second explanation fits perfectly. If you want to picture it, imagine a football thrown by someone who has absolutely no idea what they are doing. Not a clean spiral, but a ball going end over end and sideways at the same time, lurching through the air. That is more or less how this asteroid moves through space. And I know that sounds like a small, technical detail, the kind of thing you would nod at and forget. It is not. It is one of the most revealing things we know about Apophis, because of what a tumble like this actually tells us. The way a body rotates is set by how its mass is arranged on the inside. That is the key. A smooth, uniform, evenly packed, solid tumbles one way. A lumpy, uneven body, with denser regions gathered in one place and looser, emptier pockets in another, tumbles differently. The rotation is a readout of the interior. So when an asteroid's spin does not match what you would predict for a nice uniform rock, that is not a signal of anything supernatural, and it is not a glitch. It is a fingerprint. It is the hidden interior of the object leaving its signature in the motion, writing out its own irregular structure in the way it rolls through the dark. Apophis, in other words, is telling us about its insides by the way it stumbles across the sky. This is the detail that has lit up so much of the conversation about Apophis online. There is a theory circulating right now that points straight at the spin of this asteroid, argues that the motion does not match a solid body, and concludes that something inside the rock is actively shifting or changing. Now, I want to be careful and fair here, because there is a real thing and an overreach tangled together in that claim. The specific numbers being passed around online are not ones I would trust, and you should treat them with caution. But the instinct underneath the claim, the raw intuition that the strange spin means a strange interior, is actually pointing at something true. An irregular tumble is exactly what you would expect from an uneven, loosely packed pile of rubble. The spin is one of the only windows we have into the part of Apophis we cannot see. And through that window, the message is consistent. The inside of this thing is not simple. So now we have three pieces of the same puzzle, and they all say the same thing. The density says it is nearly half empty. The shape says it is two weak piles joined at a fragile seam. And the spin says its interior is uneven and lopsided. Every measurement we can take of Apophis points toward a loosely held, irregular, structurally delicate body, which raises the obvious and slightly unsettling question. What exactly happens when you take a loosely held, lopsided pile of rubble with a weak point built right into the middle of it, and you squeeze it with an entire planet? The force at the center of this whole story is one you already know intimately, even if you have never thought about it this way. It is the same force that raises the ocean tides twice a day, every day, all over the world. Gravity gets weaker with distance. That is the entire trick. So when Earth pulls on an object as large as Apophis, the near side of the asteroid, the side facing us, gets pulled just a little harder than the far side. The whole body feels itself being stretched, gently, along the line pointing toward Earth. On our oceans, that same uneven pull is what lifts the water into the bulges we call high tide. It is a familiar, gentle force, one we barely think about as we watch the sea rise and fall. But that same force, given a strong enough grip, is one of the most powerful shaping tools in the entire solar system. It is what tore a comet to pieces, when it strayed too close to Jupiter. It is what keeps our own moon locked so that it always shows us the same face. Tidal force is patient and quiet, and then, at close enough range, it is not quiet at all. And on a loosely bound asteroid passing only 31,600 kilometers overhead, that stretch becomes something far more interesting than a tide. Here is where it gets genuinely clever, and a little unnerving. Remember that Apophis is not just sitting there getting stretched. Apophis is tumbling the entire time. So as it rolls and wobbles through its closest approach, different parts of the asteroid keep swinging into that line of maximum stress, over and over, during the hours it spends near us. Earth does not pull on Apophis once and let go. It works the asteroid. The best way I have heard it described is that our planet's gravity needs this thing, the way a pair of hands works a lump of dough, pressing and stretching and turning it, hour after hour, as it passes. So what do scientists actually expect to happen when that kneading begins? This is where careful modeling comes in. Research groups have built virtual versions of Apophis inside their computers, whole asteroids assembled out of thousands of individual particles, and then run the 2029 encounter to see how those simulated rubble piles respond. And they agree on the headline: the asteroid's spin will change. Not maybe. It will change, and it will change enough for us to measure it. Apophis will most likely stay a tumbler, but its rate of spin could roughly halve, or it could roughly double, and the direction it points could shift entirely. The rhythm we spent years measuring may not survive the encounter intact. Now, I do not want to oversell the physical drama here, because honesty is the whole point of a channel like this. The actual squashing, the physical deformation of the body, is predicted to be small, on the order of centimeters, and mostly elastic. Elastic means it springs back, the way a stress ball returns to shape after you stop squeezing. The most likely single outcome is not destruction. It is a clear, measurable change in the spin, plus some small disturbances across the surface. But those surface disturbances are exactly the part worth watching, and they do not spread evenly. They concentrate. And when the models look for where the stress piles up highest, the answer comes back the same way almost every single time. It piles up at the waist, at the neck, at the fragile seam between the two lobes, the weak point we identified from the shape. The encounter could relieve the compression that has held those two lobes pressed together for ages, letting one shift slightly against the other for the first time in millions of years. It could also trigger landslides. On a body held together this weakly, even a small change in spin can set loose material sliding across the surface. And those slides could expose fresh, unweathered material that has been buried and hidden from space for an enormous span of time. We could, in principle, watch an asteroid partly resurface itself, revealing a brand new face in a matter of hours. Think about that. A world changing its appearance while we watch. Why would fresh material matter so much? Because the outer skin of any asteroid gets slowly cooked and battered by space itself. Constant sunlight, the endless stream of particles pouring off the sun, and the steady drizzle of tiny micrometeorite impacts all work on the surface over millions of years, darkening it and altering it in a process that gradually ages the outermost layer. So the top of Apophis is old, weathered, tired material, but the stuff underneath, the material that landslides could suddenly uncover, has been sealed away and protected the entire time. If parts of the surface slide during the flyby, our telescopes and our spacecraft could get a look at chemistry and texture that has never once been touched by the outside world. It would be like an ancient sealed room being cracked open, except the room is a mountain of rubble, and the crack happens in real time, in front of an audience of billions. That is not a small scientific bonus. That is a genuinely new kind of observation, and Apophis may hand it to us for nothing. Everything I have just described, though, still lives inside a range of maybes, and the reason for that vagueness is the same reason it always is with this asteroid. The models are only as good as their assumptions about the interior, and the interior is the thing we are trying to figure out in the first place. So the honest summary is this. The most likely story is a measurable change in spin, a bit of harmless flexing at the neck, and perhaps some sliding at the surface. The dramatic story, a large spin flip and a partly new face, is entirely possible if the inside is weaker than we hope. And the boring story, in which almost nothing visible happens, is possible too if it is stronger. We are holding all three at once, and only the asteroid can choose between them. Now, there is a hard physical reason Apophis is not simply going to fall apart during all of this, and it is genuinely worth understanding, because it is the thing that separates the honest science from the panic. There is a line in space called the Roche limit. It is the distance inside which a body held together only by its own gravity would be torn apart by tidal forces. Cross that line, and the stretching wins, and the object comes apart. For Earth, and for a body as light as Apophis, that line sits at around 18,000 kilometers from the planet's center. Apophis passes at about 38,000 kilometers from the center. It stays well outside the line. It enters the zone where it gets stressed, needed, and disturbed. It does not enter the zone where it gets dismantled. That is the reassurance, and it is a real one. But notice something. That reassurance answers the wrong question. It tells us the asteroid survives. It does not tell us how much it changes. And the change is the entire story. Because the amount of change depends completely on the one thing we still cannot see. It depends on the interior. So before we get to the part where the whole world is watching, we have to deal with the loudest, most dramatic version of the story, the one you have almost certainly seen online. Because it takes everything we just discussed and pushes it right off a cliff. You may have already run into the far more dramatic version of this story circulating online, and I want to walk through it with you honestly, because it is a perfect example of how a real piece of science can get bent into something it is not. The claim goes like this: Earth's gravity flexes that fragile neck over and over until Apophis breaks cleanly in two. And then the story continues. One of those newly separated pieces slips through what is called a gravitational keyhole, a narrow region in space where the exact pull of Earth would nudge that fragment onto a new path, setting up a future impact that the whole intact body was always going to miss. It is a genuinely cinematic idea. The asteroid we declared safe tears itself apart, and one of its own broken halves becomes the threat. I want to be fair to this claim because its kernel is real, and I never want to be the person who mocks a good instinct. Necks really are weak points. We have established that beyond doubt. Contact binaries really can come apart under tidal stress, in the right circumstances. The underlying intuition that the weak seam is where trouble would start is not crazy at all. It is actually good thinking. The problem is not the instinct. The problem is that the science simply does not support the leap from there to catastrophe, and it fails at several steps at once. Let me walk you through why. First, the detailed modeling, the same simulations that predicted the spin change, predicts only that centimeter scale, reversible flexing at the neck. It predicts a gentle bending that springs back, not a break. Second, and this is the big one, Apophis passes outside the Roche limit, the line we just talked about. Gravity alone cannot pull it apart at that distance. The math does not allow it. And third, even if you grant the extreme case, even if you imagine against the modeling that the neck did somehow give way, the two lobes would then drift apart at a few centimeters per second at most. A few centimeters per second. over the hours of the encounter that adds up to a separation of a few meters. And a keyhole, the narrow region that fragment would need to thread, is less than a kilometer wide, and the combined body was already precisely measured to miss it. So you would need a broken piece, drifting a few meters, to somehow find and thread a target under a kilometer across that the whole asteroid already sails past. When you stack all of those unlikely steps on top of each other, the probability does not just shrink, it collapses towards zero. The impact stays ruled out for a century. The viral version takes a real mechanism, the weak neck, and turns the dial far, far past what the data will allow. So, if the asteroid is not going to break, and it is not going to hit us, and even the scary online version falls apart under a close look, then why did I tell you at the start that the people who study this thing are quietly on edge? Here is the honest answer, and it is more interesting than any keyhole. What has scientists tense is not any single prediction. It is the spread of the predictions. It is the width of the range of possible outcomes. Because every one of those careful models had to assume something about the interior of Apophis, the one thing we have never been able to measure directly. Watch how that assumption drives everything. Feed the models a stronger, more tightly bound interior, and you get the gentle version. A small spin change, a few centimeters of flex, and almost nothing else. Feed those same models a weaker, looser, more lopsided interior, and you get the dramatic version. A large spin flip, real shifting at the neck, visible landslides, and a fresh face we have never laid eyes on. Same asteroid, same flyby, same gravity. Wildly different outcomes, and the only variable that changes is the nature of the inside, which we are guessing at. The models cannot tell us which one we are going to get. They can only hand us the range and shrug. The asteroid itself is the only thing that knows, and it will only tell us by how it behaves in the moment Earth squeezes it. I find this genuinely refreshing, and I want to be honest with you about why. So much of what gets said about asteroids online is dressed up certainty, a confident voice telling you exactly what is going to happen and exactly who is hiding it from you. The real science here is the opposite of that. The people who know the most about Apophis are the ones most willing to say, plainly, we do not know how much it will change, and we will not know until it happens. That is not weakness. That is the honest edge of human knowledge, and it is a far more interesting place to stand than any fake certainty. We have measured this rock well enough to promise you it will not hit us, and we have measured it poorly enough that we cannot promise you what it will look like the morning after. Both of those things are true at once, and holding them together is the whole point. And that is what makes this so unusual. Apophis is about to answer a question we have been asking for more than 20 years, the question of what it is truly made of on the inside. And it is going to answer it not with a calculation, but with a demonstration. A big, surprising change will tell us the interior is weak and strange. A barely detectable one will tell us it is stronger than it looks. Either way, the moment of the flyby is the moment the answer finally comes out. That is why this is not something we can settle in advance from a computer. We have to be there. We have to watch. Which raises the single most important question left in this entire story. When it happens, who exactly is going to be watching, and how closely? For nearly every close encounter in the entire history of the solar system, nobody was there to see it. Rocks have swung past planets, grazed moons, and threaded between worlds for 4.5 billion years with no audience at all. In 2029, that changes completely, because for the first time, we are not going to sit back and observe from a distance. We are sending hardware out to meet Apophis. We are putting instruments right up against it. And the story of the first spacecraft is one of the great second acts in the history of space exploration. You may remember a mission called OSIRIS-REx. It was the NASA spacecraft that flew all the way to the asteroid Bennu, the one whose surface behaved like a pit of plastic balls, grabbed a sample of it, and then parachuted that sample down into the Utah desert in 2023. It was the first American asteroid sample ever brought back to Earth, a genuine triumph. And here's the wonderful part. That spacecraft did not shut down after it dropped off its cargo. It was still perfectly healthy, still flying, still fully capable. So NASA gave it a new name and a new target. It is now called Osiris Apex, and its entire remaining purpose in life is to chase down Apophis. The way it arrives is precise enough to sound like something out of science fiction. Osiris Apex is timed to reach Apophis right around the close approach, trailing about an hour behind the asteroid as the whole system sweeps past Earth. Then it does something elegant. It uses Earth's own gravity as a slingshot to catch up with the asteroid about a week later. From there, it settles in for roughly 18 months, mapping the surface in detail, reading the chemistry of the rock, and watching how the asteroid turns. And it is going to do one thing that matters more than anything else for the story we have been telling. It will descend to within about 5 meters of the surface and fire its thrusters straight down, blasting away the top layer of material to expose the fresher, hidden stuff underneath. Sit with the timing of that. After I have spent this whole time telling you that the inside of Apophis is a sealed box we cannot open, this is the spacecraft that flies down and deliberately blows the lid off a corner of it, on purpose, to see what has been hidden. There is something almost poetic about which spacecraft gets to do this. The machine that will fly down and expose the hidden interior of Apophis is the very same one that already reached out and touched Bennu, the asteroid whose surface swallowed it like a pit of plastic balls. It has done this before. It has felt firsthand how soft and strange these rubble worlds really are. And now it is being sent to the most famous one of all, at the most important moment in its history, carrying everything it learned the first time. A retired mission, given a second life, and pointed straight at the object we most want to understand. If it works, we will not be inferring the interior of Apophis from clever guesses about density and spin. We will be reading it directly from a corner blasted open on purpose, and it will not be working alone. The European Space Agency, working together with Japan, is building a second mission called Ramses, and it has a different job that is every bit as important. Ramses is designed to launch around 2028 and to arrive at Apophis in February of 2029, about 2 months before the encounter. That early arrival is the entire point of the mission. Ramses gets there ahead of time so it can measure the asteroid in its undisturbed state, the before picture, and then ride along to record the after. And if you have ever run an experiment, you know why that matters more than anything. A result only means something if you know the starting condition. You cannot say how much something changed if you never measured what it was to begin with. Ramses is the baseline. Ramses is the control. Between these two spacecraft, one measuring the before and one probing the after, we are going to get a detailed before and after portrait of an asteroid being physically reshaped by a planet. Something that has never once been done in the history of our species. But the most numerous instruments watching that night will not cost a single dollar to build, and you may already own a pair. They are human eyes. While the spacecraft do the precise, careful science, roughly 2 billion people across Europe, Africa, and Western Asia will be able to simply step outside and watch Apophis move across the sky, brighter than the stars of the Big Dipper, over the course of one single night. And behind the crowds, and behind the spacecraft, the professional observatories of Earth will be locked on and waiting. Powerful radar dishes will hammer Apophis with radio waves during the closest approach, reading its shape and its spin in fine detail. The very same technique that first revealed its 2 lobes, now trained on it during the exact hours it is being stressed. Telescopes will track its brightness for the subtle flickers that betray a changing spin or a patch of freshly exposed ground. Between the naked eyes, the spacecraft, and the radar, Almost nothing about that evening is going to go unrecorded. These are the detectors, all of them, wired up to the same enormous experiment. And the only reason the experiment is worth running is that this time, finally, we are in position to read the answer the asteroid gives us. Which leads to the last question, the one that quietly explains why so many serious people treat this single flyby as a gift. There is a practical reason that the people who study this treat 2029 as a gift, and it reaches far beyond this one rock passing in the night. Somewhere out there, right now, is an asteroid that will not miss. It is on a date nobody has circled yet, a collision we have not found because we have not looked in the right place at the right moment. This is not fear-mongering. It is simply the arithmetic of a solar system that has been throwing rocks at planets since it formed. And if we ever have to push such an object off a collision course, to nudge it away and save a city or a coastline or something larger, the single most important thing to know, before we do anything else, is what that object is made of on the inside. Because you cannot move a rubble pile the way you move a solid rock. We have already taken the very first step toward learning how to do this, and the result proved the point in a way nobody fully expected. In 2022, NASA flew a spacecraft called DART straight into a small asteroid moonlet named Dimorphos on purpose, and successfully shifted its orbit. It was the first time in all of human history that we deliberately moved a celestial body. We reached out across space and changed the path of another world. That alone was extraordinary. But the real lesson was hiding in the details of how it happened. Dimorphos turned out to be a loosely bound rubble pile, just like the kind of object we have been describing this whole time. And when the spacecraft struck it, it did not simply dent it. It splashed. The impact threw out an enormous plume of debris, and that spray of material actually pushed the asteroid harder than the collision by itself ever could have. The softness of the body did not weaken the push. It changed the entire physics of it. Think about what that means for the future. Hit a solid rock, and it moves like a solid rock, cleanly and predictably. Hit a loose pile of gravel, and it might absorb the blow, or splash and get shoved harder than you planned, or break into pieces that all keep coming towards you. You cannot plan that maneuver. You cannot bet a city on it without knowing the interior of the thing you are trying to move. And the interior is exactly what Apophis is about to reveal, for free, in front of the entire world. The lesson our planet hands us in 2029, when it squeezes this asteroid and shows us how it responds, is the very same knowledge we would need to protect ourselves from the next one. The one that is not going to be so kind about its trajectory. This is why the people who work in planetary defense do not talk about Apophis with fear. They talk about it with something closer to gratitude. For decades, the hardest part of preparing for a real threat has been that we could never practice on anything. We could model impacts on computers. We could run the equations. But the solar system almost never lets us watch a large rubble pile get physically stressed by a planet up close, with all our instruments ready and pointed at it. Now, it is going to happen on a scheduled date, at a known object, with years of warning to prepare. Every landslide, every degree of spin change, every centimeter of flex at that neck teaches us how these bodies actually behave under force, rather than how our equations guess they behave. And there is a real gap between those two things, as Dimorphos proved when it splashed instead of simply moving. Apophis is the rehearsal we were never able to schedule, arriving right on time. So here is where all of this leaves us, standing and waiting for a date on the calendar. Apophis is the most studied, dangerous asteroid in history. Its orbit is locked down, understood to the kilometer, and it is not going to hit us. But it is also, at its core, a sealed box, a loosely bound pile of rubble, nearly half empty, built from two weak lobes joined at a fragile seam, tumbling through the dark with an interior no human being has ever measured. And in 2029, our own planet is going to run the one experiment capable of finally opening that box. The spin change, the behavior of the neck, the landslides, the possible new face, all of it will be measured by 2 spacecraft and witnessed by 2 billion people. And the asteroid's own response will tell us, at last, what it truly is. The one honest piece of uncertainty that remains is not some hidden danger being kept from you. It is simply that the interior is unmeasured, and that there is a small chance an undetected object could nudge the asteroid's path very slightly before 2029. That is the real frontier of what we know. It is not a cover-up. Everything about this asteroid has been published in the open, in plain sight, which is precisely why we are able to tell you with confidence that the orbit is safe and the object is still a genuine question. And I find something almost reassuring in that. We are not frightened of Apophis. We are fascinated by it. We have measured its path so well that we can stand here, years in advance, and invite the whole world to look up on one specific night without any fear at all, and instead feel something closer to wonder. So, mark the date. The 13th of April, 2029. On that night, a mountain of rubble that has kept its secret for millions of years is going to pass beneath our satellites, and our planet is going to reach out and squeeze it. And for the first time, we're going to find out what is really inside by watching how it flinches. The closest asteroid in recorded history is coming. It is acting stranger the harder we look, and the whole world is going to be looking right